Hi, and welcome to my next installment in this algebra and pre-calculus video series. This is part 2 of this video, graphs of the other 4 trig functions. In the previous video, we talked about the tangent and the cotangent function. So now let's talk about the secant and the cosecant functions. I'm going to start with the cosecant function. So there is a relationship here between the cosecant function and the sine function. Because the definition of the cosecant function, well, the cosecant is 1 divided by the sine function. The cosecant is the reciprocal of the sine function. So to come up with the graph of the cosecant, let's start with the graph of the sine function over here on the right. Right? So the sine function goes from 0 to 2 pi, maximum at 1, minimum at -1, right? X-intercepts at 0, pi, and 2 pi. And so hopefully this is a graph we're familiar with. We've talked about this in the previous few videos. And so let's talk about the cosecant function. Well, based on our understanding of vertical asymptotes come from when the denominator of a fraction is equal to 0. Right? So every time the sine function is equal to 0, the cosecant function has a vertical asymptote. So if we come over here, look at the sine graph. Right? As we approach 0 from the left, or sorry, from the right, as we approach 0 from the right, the y values are positive, but they're getting really, really small. They're getting closer and closer to 0. So 1 over a small number, as the denominator gets really, really small, this fraction goes to infinity. So we could think about this at each of these x-intercepts, at 0, at pi, and at 2 pi. So whenever the sine function has a 0 or an x-intercept, the cosecant function is going to have a vertical asymptote. Okay, so let's throw in some asymptotes there. All right, so now we have the sine function, and we have some vertical asymptotes. Right? So here, as the y values get really small, but are positive, the cosecant function should be going to positive infinity. Yeah, it's a better infinity sign. Okay, over here, as the y values again are getting small, but positive, the cosecant function should again go to infinity. Okay. Over here, as the y values are getting small, but they are negative numbers, so 1 divided by a negative small number is a really big negative, so that's going to negative infinity. And same thing here at 2 pi, as the y values of the sine function get really small negatives, the cosecant function will have y values that are really big negative numbers. All right, so this is the end behavior at each of the asymptotes. Now, let me switch to a different color here. When the sine function is equal to 1, right, at this point, and -1 at this point, well, the reciprocal of 1 is 1, and the reciprocal of -1 is -1. So the cosecant graph is also equal to 1 when the angle is pi over 2. And the cosecant function is also equal to -1 when the angle is 3 pi over 2. Okay, so now that we've examined what's happening close to the asymptotes and we have a couple of points, we could think about what's happening on the cosecant function, right? 1 over the sine function. Well, all of the sine values, all of those y values on the sine graph are from -1 to 1. So if you take the reciprocal, of a number smaller than 1, you get always a number bigger than 1. All right, so the cosecant graph will end up looking something like this, the blue one. Goes up to infinity. At these two asymptotes, it goes to a negative infinity at these two asymptotes. All right, so that blue graph, at both parts of it, are the graph of the cosecant function. All right, so if we're going to graph the cosecant function, it makes sense to use this relationship with the sine function. All right, so to graph a cosecant function, 90% of the work is graphing a sine function. Okay, so let's see what that looks like. And just like all of the other graphs, we've talked about the sine, the cosine, the tangent, and the cotangent previously. Right, this was the graph on the previous slide, this one period of the cosecant function. And this repeats to infinity and to negative infinity. So to the right, to the left, this one image is being repeated. Okay, so now let's talk about, now that we've examined what the graph of the cosecant function looks like, y equals the cosecant of x, let's look at some more complicated versions or more involved versions of the cosecant function. So a change in amplitude, a change in period, and a change in phase shift. So if we look at step number 1, to graph the cosecant function, the first step is actually to graph a sine function, because these two are very much related to each other. So to graph a cosecant, we start off with a sine function. Wherever the sine function has an x-intercept, the cosecant function has a vertical asymptote. Whenever the sine function has an x-intercept, the cosecant function has a vertical asymptote. And then we've got, sorry, I went ahead too quickly there. Then we got the maximums and the minimums. So the relative maximums of the sine function are going to be the relative minimums of the cosecant function and vice versa. The relative minimums of the sine, the relative maximums of the cosine. Let me go back one slide. Nope, 2 slides. Yep. All right, so I'm looking right here. When the sine function has a relative max, the cosecant has a relative min. And when the sine function has a relative minimum, the cosecant function has a relative maximum. All right, so let's see what this looks like when we're graphing a cosecant function. So let's graph one period of the function y equals 4 times the cosecant of x. So step one in this process of graphing the 4 times the cosecant of x, step 1 is graph y is equal to the sine. 4 times the sine of x, right? We want to graph 4 times the cosecant of x. So let's graph 4 times the sine of x, because the cosecant and the sine function, these are reciprocals of each other. All right, so let me go to the next slide. Here is the graph of 4 times the sine of x. Right? This wave function goes from 0 to 2 pi. And with an amplitude of 4, we see the y value of the maximum is 4, and the y value of the minimum is -4. Okay, so step 1, graph the sine function. And now, wherever the sine function has an x-intercept, the cosecant function will have a vertical asymptote. So we'll graph the sine function first, and then we'll put in those vertical asymptotes. The maximum of the sine function is the relative minimum of the cosecant. The relative minimum of the sine function is the relative maximum of the cosecant function. And we know the cosecant function approaches positive infinity to the right of the first asymptote, to the left of the second asymptote, and then approaches negative infinity to the right of the second asymptote and to the left of the third asymptote. And just like the sine function is smooth and continuous, the cosecant function will do the same. Smooth and continuous. And so this blue one it's not a parabola. It looks sort of like a parabola, but it's not actually a parabola. But these two pieces, there's one on the left and this one on the right, collectively, those two pieces make up the graph of the cosecant function. All right, so we use the sine function as a framework for the cosecant function. And we do that because the sine function is the reciprocal of the cosecant, and the cosecant is the reciprocal of the sine function. And in exactly the same way that the sine and the cosecant functions are related, the cosine and the secant functions are related. So when we want to graph y equals the secant of x, well, the definition of the secant function is the reciprocal of the cosine function. So we start with the graph of the cosine function. 0 to 2 pi, cosine starts at 1, goes to 0, down to -1, up to 0, and then up to +1. Right, so to graph a cosecant function, we use the sine function. To graph the secant function, we use the cosine function. And by the same reasoning as we talked about with the cosecant function, whenever the cosine is 0, we get a vertical asymptote of the secant function. All right, so this is our framework right here. This is our framework for the secant function. We start with the cosine function, where the cosine is 0. The secant has a vertical asymptote. where the cosine has a maximum, the secant function has a minimum. Where the cosine function has a minimum, the secant has a maximum. And so we can do the same thing. Now it's a little bit less intuitively straightforward with the secant function because one of those pieces is split in half. If we look at the interval 0 to 2 pi, right? If we look at the interval 0 to 2 pi, since the cosine function starts up here at 1, the secant function starts up here at 1 and goes up, right? But this is just one period, right? This is one period, 0 to 2 pi of the secant function. Now, the secant function, just like the other, this is our sixth trig function, and just like the other 5, this graph of the secant function, this one period repeats infinitely many times to the right and to the left. To the right of 2 pi and to the left of 0. So when we talk about the graph of the secant function, it actually looks just like the cosecant function. Right? If we look just at that part, that's 0 to 2 pi. So that's this green right here, this green right here, and this green right here. Right, so that's the interval 0 to 2 pi, or basically one trip around the unit circle. All right, so now that we have our graphs of the basic cosecant function and secant function, y equals the cosecant of x and y equals the secant of x, now we could talk about some more complicated versions of these functions. So we started off, this is a couple of videos back, we started off talking about graphing a times the sine of bx plus c. And in that same video, we talked about the graph of a times the cosine of bx plus c. Then in the next video, the one right before this one, part 1, we talked about y equals a times the tangent of bx plus c. We talked about y equals a times the cotangent of bx plus c. So we have 4 down, 2 to go. All right, so now let's look at the secant function where there's a change in amplitude, change in period, change in phase shift. And we're going to approach this in the same way, that we graph the cosine function. So that's actually step 1. Replace secant with cosine and make the graph. All right, so let's look at this guy right here. Graph the function y is equal to negative 1/3 times the secant of 1/3 x. Negative 1/3 times the secant of 1/3 x. Well, step 1 is to graph y is equal to negative 1/3 times the cosine of 1/3 x. So we talked about the change in amplitude. So instead of this graph going up to +1 and down to -1, its maximum is 1/3, or on this graph, I have it labeled as a decimal 0.333, but that's 1/3, and down to negative 1/3. Right? So we use the cosine function as a framework. Right? So wherever the cosine function has an x-intercept, wherever the cosine function has an x-intercept, the secant function has a vertical asymptote. So once we have this, we're able to draw the graph of the cosecant, or sorry, of the secant function. Right? The minimum of the minimum of the cosine is the maximum of the secant. The maximum of the cosine is the minimum of the cosecant. So the cosecant graph is going to do something like that. It's going to do something like that. It's going to do something like that. Oh, sorry, not there. Something like that. All right, we know the end behavior, which is what's happening at the asymptotes. So the graph of negative 1/3 times the secant of 1/3 x will look something like this. Notice the period is not 0 to 2 pi, it's 0 to 6 pi. Period is 0 to 6 pi. Right? And again, this is something we've discussed previously. So the period is equal to 2 pi divided by b, which in this case is 2 pi divided by 1/3, which would be 2 pi times 3/1, which is 6 pi. Right, so we have a change in amplitude. We have a change in period. And we've got a negative out front. So that's a reflection over the x-axis. Reflect over x axis. So we make these changes to the function y equals the cosine of x, right? Actually, let me write this in red, because that's that red graph. So we take the cosine function, we change the period, we change the amplitude, and we reflect over the x-axis. We get this red graph. And once we have that, then our final step is to draw in the graph of the secant function. Right? So it's very difficult to graph the secant and the cosecant functions without really understanding how to graph transformations of the sine and the cosine functions. All right, let's look at another one of these guys. Oh, I think that's the last one. Let me just double check. Yep, okay. Well, that's it for this video. I thought I might have had one more, but I don't. But let me go back a couple of slides. Right? And this is really what I want to focus on. Right? if your goal is to graph the secant function, you start off by replacing SEC right here. Right? You replace the secant with cosine. Right? If you're starting with secant, you graph the cosine function. And similarly, let me go back a few more slides. If your goal is to graph a cosecant function, step one is to graph the corresponding sine function. So when you graph the sine and the cosine, the x-intercepts become asymptotes. Maximums become minimums, and minimums become maximums. And once you have all of that, then you're able to graph any version, any transformation of either the cosecant function or the secant function. All right. That does it for this video. I hope this was helpful.